We are reading chapter 25, section 3 on page 664. Have you ever gone outside after a rainstorm and noticed how clean and fresh the air smelled? Most of the time, people don't think about air. However, air contains substances that all organisms need to survive, including nitrogen, oxygen, carbon dioxide, hydrogen, methane, and ozone. Water vapor can make up as much as 5% of air by volume. For humans and other animals, the most important component of air is oxygen. Oxygen makes up 21% of air. Origin of oxygen. Most organisms on Earth require oxygen or carbon dioxide to maintain their life processes. Oxygen has not always been a part of Earth's atmosphere. Scientists hypothesize that 4.6 to 4.5 billion years ago, Earth's atmosphere was similar to the mixture of gases released by erupting volcanoes. These gases include carbon dioxide, nitrogen, and water vapor. As Earth cooled and became more solid, rains washed most of the carbon dioxide out of the atmosphere and into the oceans. Early life forms in the seas used carbon dioxide during photosynthesis and released oxygen and water vapors. Over time, oxygen in the atmosphere built up the levels that allowed the evolution of organisms that require oxygen for life's processes. Disrupting Earth's cycles. The geochemical cycles of Earth's atmosphere are in a delicate balance. Volcanic eruptions release various gases and dust particles into the atmosphere. Photosynthetic organisms in the oceans and on land take in and use carbon dioxide and release oxygen. Other organisms take in this oxygen and release carbon dioxide. Life on Earth continues to survive as a result of the balanced gas exchange. However, human activities are disrupting these cycles. For example, humans burn fossil fuels to produce electricity and burn forests to clear land. These two activities release carbon dioxide into the atmosphere. Increased amounts of carbon dioxide are thought to play a role in global warming, which is the gradual rising of Earth's average surface temperature. The human alteration of carbon cycle has the potential to change global climate and therefore the environments of food-producing regions. Rainfall patterns in the tropical rainforests of the Amazon River Basin have already changed as a result of the loss of forest cover. Some of these rainforests is shown in figure 2512. You will find out how deforestation is affecting tropical rainforests worldwide in the problem-solving lab on the next page. Humans also disrupt other geochemical cycles. By burning fossil fuels and using fertilizers that contain nitrogen, humans release about 3 times as much nitrogen oxide and ammonia gas into the atmosphere as do the natural processes of the nitrogen cycle. In the atmosphere, nitrogen oxides are converted to nitric acid, which returns to Earth in acid precipitation and damages surface water, plants, and soil. Human activities also release sulfur into the atmosphere when coal and oil are burned to produce electricity. Sulfur in the atmosphere is converted to sulfuric acid, which also returns to Earth in the form of acid precipitation. Both the excess nitrogen oxides and sulfur are pollutants, which are substances that can adversely affect the survival, health, or activities of organisms. These are only a few of the chemicals that human activities release into the atmosphere. Small amounts of toxic metals such as lead, cadmium, and arsenic also are released. When pollutants in the air occur in quantities that become harmful to human health and the health of the environment, air pollution results. Sources of air pollution. Air pollution have both natural and human origins. 2 natural sources of air pollution is shown in figure 2513. Human sources of air pollution include gases, smoke, and dust. One of the biggest sources of air pollution is the burning of fossil fuels. Power plants that generate electricity burn coal and oil, which produce many types of air pollution. However, the single largest amount of air pollution in the United States is the exhaust from motor vehicles that burn fossil fuels in the form of gasoline. In the United States, motor vehicles cause 90% of the carbon monoxide pollution in cities. In cities such as Los Angeles, Rome, and Mexico City, shown in Figure 25.14, motor vehicles are responsible for 80 to 88% of the air pollution. Air pollution can make humans ill. When humans inhale harmful gases, the gases can be absorbed by the bloodstream and interfere with various body systems. Carbon monoxide, a colorless and odorless gas, interferes with the body's ability to absorb oxygen and causes headaches and chest pains, dry throat, and nausea. Pollution can also cause burning eyes, irritated throats, and breathing difficulties. Some chemical air pollutants can cause cancer, birth defects, brain damage, and long-term injury to lungs or even death. As clear air in the troposphere moves across Earth's surface, it collects both naturally occurring and human-made pollutants. What happens to these pollutants? They may be transported, diluted, transformed, or removed from the atmosphere. Transformation and dilution. Some pollutants may be carried downwind from their origin. Transport depends upon wind direction and speed, topographical features, and the altitude of the pollutants. For example, hills, valleys, and buildings interrupt the flow of wind and thus influence the transportation of pollutants. Many of the pollutants in the acid precipitation that falls in the Adirondack Mountains of New York State were transported from coal-burning power plants in the Midwestern states. If the air movement in the troposphere in turbulent, some pollutants are diluted and spread out, which reduces their concentration. Transformation and removal. Other pollutants undergo chemical changes called photochemical changes that are triggered by reactions with ultraviolet radiation. Photochemical smog, for example, forms when a mixture of nitrogen oxide and volatile organic compounds interact under the influence of sunlight. Some other air pollutants undergo physical changes. For example, dry particles may clump together and become heavy enough to fall back to Earth's surface. These and other air pollutants are removed from the atmosphere in precipitation, which includes snow, mist, and fog, as well as rain. Indoor air pollution. Have you ever stopped at a fabric store? Some people cannot even enter such a store because they are sensitive to the chemical formaldehyde, which is used in fabrics to prevent damage from insects. About 90% of the furniture sold in the United States also contains formaldehyde. Formaldehyde is just one of the many air pollutants that occur indoors, as shown in Figure 25.15. Sick buildings. Studies conducted by the United States Environmental Protection Agency and by scientists in European countries have linked indoor air pollutants to headaches, coughing, sneezing, burning eyes, nausea, chronic fatigue, and flu-like symptoms. When these symptoms are experienced by 20% of the occupants of the building is said to be sick. Often these symptoms disappear when the affected people go outside. New buildings are more likely to be sick than older buildings. This is because newer buildings tend to be airtight so that heating and cooling costs can be kept to a minimum, and because new furniture and carpeting release many indoor air pollutants, including styrene and formaldehyde. Radon gas. The gas known as radon-222 is colorless, odorless, tasteless, and naturally occurring. Radon-222 is produced by the radioactive decay of uranium-238. Small amounts of uranium-238 are found in most soils and rocks and in underground deposits. Usually, radon gas from such deposits seeps upward through the soil and is released into the atmosphere, where it is diluted diluted to harmless levels. However, when buildings are constructed with hollow concrete blocks or when they have cracks in their foundations, radon gas can enter and build up into high levels indoors. Once indoors, radon gas decays into radioactive elements that can be inhaled. Scientists have traced approximately 13,000 lung cancer deaths in the United States each year to high levels of radon gas in homes. Because it is impossible to see or smell a buildup of radon gas in a building, the EPA suggests that people test the radon levels in their homes and offices. Radon test kits, such as the one shown in Figure 2516, measure the levels of radon in a building. Are you letting me stop?